yourselves just what integration is, we've been instructed to take a drive around and record the speedometer and odometer readings. The first trip was way too long and there were way too many data points to work with. The second go-around was much more reasonable. I took down 45 readings in 5-second intervals. The first step was to convert these readings from miles per hour to feet per second. I found the conversion constant and multiplied each value by 1.46, repeating. This produced these values, which I then rounded to the first decimal place. The next step is to graph these values. The y-axis is measured in feet per second and the x-axis is measured in seconds. Now is when the calculus comes in. First I drew in the left-hand sum boxes. Next I wrote out the left-hand sums and calculated them to be 7,063. I did the same for the right-hand sums, drew boxes and wrote them out, and calculated them to be 7,261. The trip odometer read to be 1.4 miles. This is equivalent to 7,392 feet. Why is this value so close to our left and right-hand sums? Physics has taught us that we can calculate a distance of a trip by finding the area under the curve of a velocity versus time graph. But why? Physics thus far has just told us to blindly believe it. Calculus can explain. The process of a Riemann sum is to break up the area under a curve into evenly spaced rectangles. The sum is the addition of the area of every rectangle drawn. Think about the sides of these rectangles. One is measured in feet per second. The other is measured in seconds. To find the area of the rectangle, you must multiply these two units together, which results in just feet. Therefore, the area represents the distance during the trip of the curve. So, the odometer reading and the left and right-hand sums are pretty close. But from what we know about left and right-hand sums, the left should be an underestimate and the right should be an overestimate. This isn't the case. Why? If I treat this like an experiment, I can assess possible errors. The main reason is that when I converted from miles per hour to feet per second, the values were almost always infinite decimals, and I only took the first. I took the average of the left and right-hand sums, and when I used it to calculate percent error, we find that I was off by 3.2%. For a simple calculus project, that's pretty good.